Hi, I'm Ray Gallucci, and I'm happy to be one of the 5 or 6 members here who have been to all four of the Chappell Natural Philosophy Society conferences. The first one was in 2015 down in Boca Raton. Then we were near the University of Maryland in 2016. Last year, we're out in beautiful Vancouver, BC, and we're here in Connecticut this year. And as I've done at the other 3, I'll be giving 4 papers. And this year, I won't be talking about much on relativity, or at least I won't be the one igniting the ether particle debate that I'm sure will come up later on. This year, I'm going to be focusing on galaxies and galactic rotation and this type of stuff. Those who know me know that I don't really have any of my own theories. I like to look at other people's theories and then try to do my little simple mathematics to see if they're plausible or not. And so the first paper is going to be cosmic expansion versus galactic density. The steady state versus the Big Bang, which are the 2 dominant theories. Obviously, I mean, the mainstream has long since put the Big Bang on a pedestal, but there are still those who will advocate the steady state, though they'll never get published in any mainstream journals. Observing galactic density with the increasing distance and correspondingly earlier times given the time travel of light should provide evidence as to whether a steady state, non-expanding, or Big Bang-driven expanding universe is the more defensible cosmology. So my thought was to simulate galactic densities for both cosmological models. And while I was doing this, I came across some work that had been done by Uri Heyman. And there's a couple of references here for his work, which I highly recommend if you're interested in this topic, you take a look. And I even corresponded with him and shared some ideas with him. And this is his dominant theory here, called the dichotomous cosmology. A universe where the material world is static and the luminous world is expanding that reconciles the static universe of Einstein with observations of the expanding universe. And if you're interested, again, here's the reference for Uri Heyman's work. If the universe is expanding, then we would expect that the galactic density back in time, that is at the greater distances, should be larger than it is closer in time at the nearer distances, because the universe theoretically was more compact. However, and this is what actually mainstream has been reporting, the teams are finding that the number of galaxies per unit of volume of space drops off smoothly with increasing distance. And this is an article, Hubble finds most distant primeval galaxies. And there's a reference there if anybody's interested in that. Contrary to, another quotation from mainstream, the expansion of the universe means that objects that were very close together at the time they emitted the light that we're now seeing are spread out over a sky in a way that wouldn't happen in a universe that wasn't expanding. And that was an article titled, Why Does the Apparent Density of Galaxies Drop Off at Larger Distances? And as usual with mainstream, when things don't align with their theories, they come up with patches. It's like cosmic inflation. They allow the speed of light to be exceeded when they need it to be, and never at any other times. And that's, I mean, that those of us here are familiar with the way mainstream operates, and since we question it, we like to look for alternate explanations. So my effort focused on 2 sets of simulations. I randomly placed 100 galaxies over a square area, and I worked in 2 dimensions rather than 3, just for visual and calculational convenience, and see if the conclusions would apply equally to 3 dimensions. For my no cosmic expansion simulation, the steady state, I chose a 6x6 grid, 36 square random units. For cosmic expansion, the Big Bang simulation, I started out with 2x2 or 4 random units, and then I could grow it, eventually going out to 6x6 because I have to expand my universe for that simulation. Within each, I place a circle whose diameter matches the sides of the square, basically just filling the circle in there, and determine how many of the 100 simulated galaxies fall within the circle. And this is a diagram of what I did for the non-expanding steady-state universe simulation. This is my 6x6 grid. The dots represent the 100 galaxies randomly spread throughout there. I just used a random number generator for the locations. And I had 3 sets of rings here because these are actually, I'm going to use these for comparison later for the Big Bang expansion. And I ran 5 sets of simulations. And I just counted up the number of, for each simulation, I counted up the number of galaxies that fell within each of the rings. And what I show here is one of the 5 simulations. This is the results for the sneak previews. This is the results for this, for the simulation results for the ones shown in red here. And as it turns out, stop that. What I label here, you'll see anything outside the 3rd ring. Anything outside the 3rd ring, I labeled as non-observable because I'm right at the center here as the observer. This is the simpler case. It involves observation and expectation at just one point in time. It turned out that a total of 41 in the 3rd ring plus 25 in the 2nd ring plus 8 in the 1st ring, or a total of 74 galaxies fell into the observable universe, which are the 3 rings. The expectation based on the area would have been 78.5 galaxies. And since this is a simulation, you don't get the exact same results, but it's pretty close, 74 to 78.5. There were 41 within the circle of radius 3, actually the annular ring between radii 2 and 3, 25 in between 1 and 2, and 8 within the innermost circle. And you can see from the table over here, if I can do this without it slowly switching. You can see here, these were the results from the averages of the 5 simulations within each of the rings. And the expectation is that there would be 2.77, the galactic density within each ring being constant should be 2.778, or 100 over 36 squares that were there. And you can see that the results came out to be pretty close to that. 2.778 on average. So for my non-expanding universe, nothing too dramatic there, just you have a nice equal spread. The galactic density is pretty much uniform with distance as you go farther out. And that's what you expect for the steady state universe. Now for the expanding universe, and you've probably seen diagrams like this where the universe starts as a singularity, then it shoots out, and then it starts gradually expanding, and the way they show it here, since supposedly galactic the expansion is accelerating. I don't know how to stop this from flickering, but since it's accelerating, you can see with the arrows that it actually gets wider and wider at an increasing rate. For the expanding universe, the case is more complex, since each simulation must represent a different time, starting from the most compressed universe at time 0, which is to the far right. I wonder if the mouse would, maybe I'll have better luck with the mouse. There it is. Let's see. Maybe it won't switch as much if I use the mouse. Okay, so at time 0, so this is, again, this is where the universe is supposedly started, and then we're going out to time 0. Then we go later in time, 0 plus and 0 plus plus, as our universe expands under the assumption of a Big Bang. Each simulation is expanded from the earliest to the latest time, corresponding to 3 views of an expanding universe as seen by an observer looking farther into the distance and earlier back in time. Now, only in this simulation, only the galaxies within the innermost circle of radius 1 will be visible at any time, because again, you've got the travel for the speed of light, the universe is going out, stuff that went out beyond the time between the distance and the speed of light wouldn't be observable until more time passes. Any galaxies outside that circle are beyond the observer's view and therefore of unknown existence. And that's the mainstream theory today, is so we can only see out to a certain distance because we have a finite speed of light. Okay. Here's the expanding universe. Again, only the innermost circle is considered to be visible in each of the examples. At time 0, the earliest time, we can only the universe is only expanded out to the first circle, first radius 1. I did 5 simulations here. So basically, I'm putting 100 galaxies into this small square area. And again, as you expected, there should have been an average of 78.5 galaxies in here. And you can see that the galactic density originally would have been around, theoretically should have been around 25 at time 0. And the simulation shows, the one in red is the one that's pictured, shows roughly about 25, so the simulation matches with expectation. As I go to the next time period, this ring where the initial set of galaxies has now moved out that farther. Now more galaxies are forming in here. This is the observable universe again within the first circle. Now we would expect the density to have dropped because the galaxies have spread farther out, and we would expect roughly about 6.25 galaxies in this inner circle. And you can see here that the density again for the simulations comes out close to the 6.25. And at the latest time, the initial galaxies have gone this far out, second set, now the third set of galaxies. Again, these are the only observable ones. We would expect down here to have about 2.8 galaxies within the inner circle, and the average is 2.4, not too bad. Simulation 2.546. So what's to note here is that if we have an expanding universe, the galactic density should, as you go farther out in time, should be dropping 25 to 6 to about 2.5. And that's what the mainstream said should be occurring. So if we do this comparison, neither universe, the non-expanding or the expanding universe, shows a smooth decrease with increasing distance back into time as expected by the mainstream. In fact, if you look for the no expansion case, which is the first case I ran, had a uniform density going out. That's shown by this bottom straight line here and the open circles. The expanding universe actually shows that as I go further back in time, greater distance moving to the right, the galactic density is much higher earlier in the universe than it is at an intermediate and current time. So neither one of them shows the expectation of some sort of decrease, which is what, again, the mainstream says should be happening. Now, if we take into account that galactic brightness, intervening dust and gases, etc., it's fairly easy to extrapolate this version of the universe, which is the steady state constant. You can see that if we allowed for some sort of decrease in visibility over distance, that this one would be easily convertible into some sort of decrease over distance. Whereas trying to make this one turn into a decrease would require drastic changes because it's actually a quite strong increasing density with time. So it is likely apparent smooth increase in the number of observable galaxies decreases with distance. That's for the observation to be true, that actually what the mainstream expects seems to actually to favor the concept of a steady state universe more so than one of an expanding universe. For this to hold for the expanding universe, the significant increasing trend would need to be overcome quite dramatically. So in conclusion, even if one speculates that there should be less galaxies in the distant past for an expanding universe as one sees deeper into space and closer in time to the alleged Big Bang, my time 0 does not necessarily represent such a distant past. I had a very high density at time 0 when I did the simulation for the expanding universe. I could consider shorter time spans, perhaps maybe a few or at most several billion years instead of the mainstream 13, 14 billion year alleged age of the universe, during which most of the galaxies would already have formed, removing the rate of galactic formation from consideration. I wasn't, if there's a strong change in the rate of galactic formation. That might be, mainstream might argue, well, that's one reason why it's not decreasing like it should be, because the rate of galactic formation was much stronger originally than it is now. And that might be one of the, I'm not sure, but that may be one of the patches that they use to show why the observations aren't lining up with their expectations. Though much simpler than the simulations performed by Heyman, and he did some very good work and very detailed work, similar simulations, my results appear to align with his conclusion. And his conclusion, observations of galactic density with distance suggest a steady state, non-expanding universe rather than one expanding as a result of an alleged Big Bang. That concludes the first talk.
You have questions? Ray, I think many of us who think about the Big Bang, I have had how do you untangle this idea that as you're looking out into the sky, you're seeing things that took a long time to get to you, and where they really are at the time you're looking at them. I have a real hard time just getting, I think this is great work, and I'm glad someone's trying to tackle it. But since you thought of it, how do I get out of my mind this problem where I'm looking at it now, and it's taken 13 billion years from it? Well, that's 13 billion years. It's now 13 billion years later than from when I saw that. How did you untangle that conceptually in your head?
Well, that was the idea. Let's see here. If I go back, that's a non-expanding. That was the idea with the non-expanding universe. Basically, I had to say I need to create two simulations, both of which, with the final step of each simulation, has to be what I see today. So here's my non-expanding universe, and what I can actually see, I mean, is really just the inner circle, but what's really out there is everything from the outermost circle. But if you accept a finite speed of light or near finite speed of light, you're kind of stuck with, you can only see as far as you've had a chance for light to travel from formation. With the expanding universe simulation, again, I use the same size, the 6x6 grid, but I start out by saying that originally this is my final universe for comparable to today's steady state, times 0 plus plus. My initial universe is here, is this smaller universe.
I'm trying to get it on the screen because what you did something that got it off the screen, so I'm trying to get it back on the screen. But keep talking, go ahead.
This is the smaller one, and so everything here is in this initial universe. Then the universe grew bigger with the 4x4, then the 6x6. But what's observable only is this period of time that basically the Earth has been in existence and light has reached the Earth. So we could only see these innermost circles in each case. So, but the comparison here is that while we see in both the non-expanding universe, we see this innermost circle, we see roughly 2.8 galaxies, density of 2.8 galaxies for my simulation. We see the same here, because this is the current time, we see the same, about 2.8 galaxies, but the difference is that in the expanding universe, at an earlier time you would have seen much denser, and so when you look back further in time, and you look back to what was the universe then, you should see a much higher density. This is what you should be seeing if the universe was expanding and you could only observe within the inner circle. So that was kind of my, I do try to simulate what really is out there that we can't see, and then how what we can see aligns with what the expectations are. And again, the mainstream expectation is that for the galaxies that are supposedly farther and farther away, and this is all based on theory of that the redshift is based on cosmic expansion and all that. And I don't necessarily buy into that. I mean, I'm a tired light aficionado, and so I don't necessarily think that the galaxies that have the highest redshifts are necessarily great distances away. And I have a paper for next year or the year after on Holt and Arb's work. But again, those in the mainstream say, well, I look farther out, I should be seeing this much greater density. They don't see that, so they need an explanation for it. And so, like I say, I can't reconcile how we handle what we can't see, but what I tried to do was say, at least based on theory, this is what should be out there. This is what I should be seeing based on what really is out there. And as a result of what I am seeing, it would appear that what should be out there is a steady state type of universe rather than an expanding universe based on these two concepts and the work that Uri Heyman did. So that's kind of how I try to handle that dilemma of time and distance.
Okay, let's see if we have
Is this
we have a question from the internet, and this is from Ken Bernhardt. He says, agreed, galactic redshift due to photon fatigue can result in a universe expanding a lot slower than expected if one does not take the presence of intergalactic gases into consideration, but are they enough to result in a steady state universe? Also, let's see here. If the universe is found to be expanding, then what is it expanding into? So that's Ken's questions.
Since I don't, that's a good, the second one is a good philosophical question. I mean, the universe is expanding. If the universe is everything and is space, how can it, what's it expanding into if it is everything? And I mean, that's a philosophical question that, again, the mainstream kind of pushes aside. As far as the first question, again, my thought was that since the two simulations, the expanding universe show that you should be seeing a much higher density back in time. The mainstream expects to see decreasing density with time, and the simulation for the steady state showed a constant density with time. So the point is that while neither the expanding universe simulation nor the steady state universe simulation showed a decrease with time, I didn't take into account changes in luminosity, etc., from possible interference from intergalactic gases and things. If I were to do that, it would be a lot easier to take the steady state universe that was constant with distance and time and shift that down a little bit and get a decrease, as opposed to taking the expanding universe that had a very rapid increase, and to turn that into a decrease. There's just no way I'd be able to argue that just some sort of light attenuation or light absorption with distance could shift that curve as dramatically as necessary in order to align with what's actually being observed. Regardless of what theory is true, I mean, what is observed is galactic density decreases with alleged distance. Again, alleged distance is because everything is based on redshift, and redshift is supposedly aligned with distance.
Okay, are you, just a real quick question, are you saying that mainstream actually says it should be dying off, which is, it seems,
Galactic density.
I mean, that is the most, from what I can understand what you're saying, that's the most extreme, difficult, almost impossible thing to happen, and yet that's what they're claiming. I mean,
yeah.
What evidence do they give?
Teams are finding, well, this was again, the teams are finding that the number of galaxies per unit volume of space drops off smoothly with increasing distance. The expansion of the universe means that objects that were very close together at the time they emitted the light that we're now seeing are spread out over the sky in a way that wouldn't happen in a universe that wasn't expanding. So they're saying that the observation, the only way they can explain that the density of galaxies is decreasing is because they're saying that the volume is getting much larger and larger. That's the only way they can explain that. So they didn't expect to see that. I believe mainstream also, part of it I think is that the rate of galactic formation was supposedly much higher originally as well. So it's not consistent for them to be seeing this decreasing density with what they claim to be distance and time. But they are seeing that, so they need to, so their explanation is that they say, well, that justifies that the universe is expanding. Same number of galaxies, but greater distance. Everything's moving away from everything.
We have another question from Bill.
The interpretation of the redshift has been flawed. The problem with it is that it's assumed to be only due to Doppler effect, but we have measured the gravitational redshift and it was never taken into account. When you do that, you find that the universe, all the galaxies that we can see, appear to be in 5 shells, and those shells obey Bode's law, just like the Bode's law that applies to our planets around the sun. And so with that, you don't get an expanding universe directly from that, but you do get an expanding universe when you look at the force of gravity is decay, and we can measure the decay. We've measured it for hundreds of years now, and it's not constant, it's decaying. And so the decay of gravity will cause our solar system to slowly increase in size over time, and presumably if all the galaxies in the universe are going around some sort of center, then they will be expanding from that center.
So there's lots of other logical explanations for what's observed. Mainstream locks into one and will not even let the other ones be aired. I mean, if you remember, I think it was 2 years ago, I gave a paper on the asymmetry of the tides, which was pretty straightforward. It didn't require any relativity or anything like that. And it looked at the numbers came out that said, the mainstream said that Earth's tides should be symmetric. High tides, if the Earth was a perfect sphere and the water was perfectly spherical, annulus around there, that the high tide should be exactly equal on opposite sides of the Earth, the low tides exactly equal. Again, anything that was diametrically opposed should be exactly equal, because mainstream says that tides are based on the differential force of gravity between the moon and the Earth. The sun doesn't really have much of an effect differential. And again, this was based on solving an approximation to the exact equations. So I went and solved the exact equations and showed that there is a bit of an asymmetry, that the tide on one side closer to the moon should be a little bit higher than the tide on the opposite side. And I sent that into the mainstream, and they came back and said, well, the expansion of a series is not an approximation, because if you go out infinitely, you get the same thing. I said, yeah, but no one ever goes out infinitely. The series approximation that this theory is based on is truncated after 2 terms, because it just so happens that truncating it after 2 terms works out to be the exact symmetry that you want. But if you solve the exact equation, I don't need to do a series expansion, because the exact equation is pretty easy to work with. I just, some quadratic formulas. You do have an asymmetry. No, you're just wrong. And so, I mean, the paper couldn't be published, even though all I did was solve a math equation, and I didn't use an approximation that the mainstream uses. So that's why I say, your theory there, the theories that Heyman have put forth, other explanations, they will not see the light of day. And there was your question earlier, you were talking about, I think, the difference between critical thinking and the mainstream. The difference is that the mainstream, when they see the topic, the title, they don't even review it. They just throw it in the trash pile. They go crackpot, crank. And that site you were talking about, the French site, which has like 6,000 dissidents, you may be on there. I'm not famous enough yet to be on there, but there's a whole bunch of people there, and it has crank, crankier, crankiest. And all, I mean, this is just a huge list of everybody. And I mean, it's just, at least it lists everybody, but I think it's like crackpot.com or something. And they say, the mainstream, they see the topic, they don't review it. I mean, it came back in 2 days just saying, this is, we don't accept this type of topic. I even ran into the progress in physics, if you're familiar with that. Steve Crothers, who's looked at Schwarzschild's original equation, showed that you do not get a singularity when you solve the equations, and it resulted from a mistake by Hilbert, et cetera, and there's no black holes. He used to get published in Progress in Physics early on. So I thought, well, maybe I'd send my title paper to them, because I thought they were open to dissidents, et cetera. Comes right back. I said, wait a minute, you guys published Steve Crothers, Pierre-Marie Robitaille, who thinks that the liquid metallic sun. I mean, you've published all these people. What's going on? And now that they've become successful over the last 15 years, I don't think they entertain dissidents anymore. And so even these organizations, these papers that start out with an open mind, eventually come around and become mainstream. I think the only one out there that'll publish things, Duncan's had some luck with physics essays, and I think Cynthia Whitney's, was it Galactic, Galilean electrodynamics, they'll still accept like that, but the mainstream doesn't review these things, doesn't even give them a chance, whereas here, I mean, I've seen flat earth papers here. I mean, I've seen hollow earth papers. I mean, obviously expanding earth papers are very popular, but I mean, if you send one of those into the mainstream, it was crackpot in the trash.
Okay, let's wrap this one up. Thank you very much. Okay, we're going to stop the recording so we can at least have them